MS Ramaya University of Applied Sciences.
Hi students, let us discuss differential pulse code modulation. The aim of the experiment is study of differential pulse code modulation. If the input is a continuous time analog signal, it needs to be sampled first so that a discrete time signal is the input to the DPCM encoder. The block diagram as follows. The apparatus required are Syntec 2113 kit with power cords, digital oscilloscope, probes and connecting cords. The connection diagram is as shown. The procedure is connect the sine wave output of the audio signal generator to one of the inputs of the difference amplifier as shown in figure 7.1. Connect the output of the difference amplifier to the input of the ADC. Connect the output of parallel to serial converter to the input of serial to parallel converter of the receiver accumulator. Connect the output of the DAC to the other input of the difference amplifier as shown in the above figure 7.1. Now switch on the power supply, observe the sine wave output of the sine wave generator on the CRO, adjust the frequency of sine wave at 1 kHz. Observe the signal at the output of DAC. You will see the staircase approximation of the input signal at the output of DAC. Also, observe the output of low pass filter and see that it is nearly same as the input signal. Now, observe various controls and clock signals shown in control and clock section and try to relate these signals with the timing diagram of below figure 7.2. Note that the sampling starts with the R bar W signal pulse that has a frequency of 8 kHz for a small duration when pulse is high. ADC reads the input port and for the rest of the low period it provides this data at the output of the ADC. Now observe the clock and reset signal of the parallel to serial converter. Observe that for the time period when reset is low, exactly 5 clock pulses shift the content of the shift register. Observe the LE2 and OE2 of previous data latch and relate them with timing diagram of below figure 7.2. You may find it difficult to appreciate the entire control signal simultaneously with a normal 2-channel CRO, but nevertheless, an initiative sense of relative time-based occurrences of all these signals can make the task easier. You can see all these signals simultaneously on the screen within the help of logic analyzer too. Also, it is to be taken into consideration that the data flow through the entire system is fast enough random as well, so it is not feasible to observe the data exactly at any point. But still, you can have an overview of the data statistics at any test point of the data bus. Figure 7.2 shows waveforms at different stages of DPCM.
Hi students, current experiment is differential pulse code modulation and demodulation. Here we are using the board 2113. This is Syntec 2113 board. Here we have the function generator which can generate between the 300 Hz to 3.4 kHz. By using this knob, I fixed it to the 1 kHz. Then it is the differential amplifier which is having the input signal as well as the feedback like predictor output. The next would be the difference signal will be fed into the analog to digital converter. The output of analog to digital converter is fed into the parallel to the serial converter. The series of bits will be fed into the serial to the parallel converter. Here the output of serial to parallel converter is fed into the adder as well as the subtractor, and the data latch, previous data latch and the data latch connection are shown in this block diagram. Then the output of these things to the digital to the analog converter, then it would be low pass filtered. The output of the low pass filter will be the regenerated, means differential pulse code modulated and demodulated. The signal we are going to get back is the whatever we are going to transmit. That would be the output of the low pass filter. And digital oscilloscope, this is digital oscilloscope. Main power switch of this digital oscilloscope is this one, and we have two channel this is a two channel oscilloscope, channel 1 and the channel 2. These are the magnitude adjusting knobs, and these are the horizontal position adjusting knobs, and this is the time scale adjusting knob. These are the connecting probes for digital oscilloscope, and these are the connecting wires for the Cytec 2151 board. Now let us start the connections for the experiment. Now let us connect the output of the function generator, that is the sine, to the signal input. Output of the difference signal is connected to the input of difference signal. Then we are going to connect DPCM signal for the transmission, would be connected to the DPCM signal in the receiver. Then we are going to connect the predictor output to the predictor input. Now let's connect the probes for the channel 1 and 2 of the digital oscilloscope. Now channel 1 is connected to the input signal, that is the from the function generator, which generates 1 kilohertz sine wave, and the other pin would be to the negative or the ground, negative of the terminal of the CRO probe is connected to the ground. Again, for the output of the low pass filter, output of the low pass filter is connected to the probe channel 2 of the digital oscilloscope, and again we are going to connect the negative to the ground. Now switch on the power supply of board as well as the digital oscilloscope. Let us press the auto set option and then press the run and stop option. Now you could able to see the sine wave of 1 kilohertz which I transmitted and coded, differential pulse code coded and decoded, and we are producing the same sine wave which we have transmitted and the received. It is one and the same. So it's this differential pulse code scheme is functioning faithfully. The inside clock signals we are going to observe now. The different clock signals, I am removing the connection from the channel 2 probe and I am going to connect the clock signal of the parallel to serial converter, and I am going to observe the signal on the digital oscilloscope by using the auto set option and run and stop. Now you could able to see the pulses like 1, 2, 3, 4 and 5 pulses in series, and rest of the time it is 0. Again it repeats. For that, if I change the time scale, okay, yeah, now you could able to see the pulse pattern. 5 pulses, after that some gap, then again 5 pulses. Then you change the clock to the OE signals. OE, it is inverted OE 1, and again you press the auto set and run and stop button. So if I change the scale now, you could able to see the pattern of pulses. Then I want to see LE, so again press the auto set and then run and stop. So you could able to see the LE signal. So there are 3 LE signal, LE1 and LE2 and LE3. These 3 signals we can observe. To see the difference between LE1 and LE2, I am connecting channel 1 probe to the LE1 signal. I am removing from the channel 1 and now I am connecting to the LE1 and channel 2 to the LE2. So again you press the auto set button and you could able to see some difference in the time where LE1 and LE2 are getting their pulses. Again you can see for LE3, removing it from LE1 and connecting it to the LE3 and again pressing the auto set button. Now I am showing the LE1 and LE3 waveforms, which is almost same. These are the clock waveforms which we can observe out of this experiment, and this completes the experiment.
At MSR, you arc your imagination further.